Solid catalysts are used in energy, chemical and environmental processes. Catalyst performance, activity, selectivity and stability is largely determined by their preparation. The catalyst synthesis may be considered as one of the most influential unit operations in industry. My lecture provides an introduction to basic concepts and research tools relevant to catalyst synthesis. How to make a catalyst? I have talked about my work to friends, and they translate my speech into their own language. Mix together a bunch of ingredients that sound exotic. Boil them for a while. Say some silly words from the book of spells, and the result is a powerful potion. My friends understand that in order to make a functional potion, I have to work hard, study, follow up on the lucky breaks, and try a lot of variation before homing in combinations that give something interesting. Despite the large number of publications and patents about the catalyst preparation, the field of catalyst synthesis method can be still considered too much an empirical art and not as sufficiently a science. Let's figure it out together. If I will talk to people about my work, they will very likely tell me that I am working in the garage. They also tell me a story about the cars. Certainly, the car's catalysts or catalytic converter is the exhaust converter representative a very effective application of catalyst. The catalytic converter effectively removes most of the car pollutants. For nearly 30 years, the automotive industry has been talking about hybrid electric vehicles and fuel cells without producing a very large market to date. In the next 20 years, we can expect to see an infrastructure that fully supports hydrogen gas production, storage, and transportation. By the 2040, you should expect a competitively priced fuel cell vehicles. We can call this car catalytic vehicle. However, catalysis has a much wide scope of application. Do you know how many industrial processes are using the catalysts? Approximately 90% of products of chemical industry are made in catalytic processes. The phenomenon of catalysis applies to a wide range of chemical reactions. By using a catalyst, non-selective chemical reaction can be made selective, and those that require a high temperature can be performed at low temperature. The catalyst offers an alternative, energetically favorable mechanism for the non-catalytic reaction, thus enabling processes to be carried out at industrially visible conditions. A key component for the development of novel processes is the development of suitable catalyst. Give me a reaction and I will tell you which catalyst you should use. And many chemists would love to say these words. It would be ideal to have a good material for every chemical process we wish to employ. Catalysis is about reactivity, catalyst synthesis, and spectroscopy. In order to understand heterogeneous catalysis, we should have a good understanding of the adsorption and desorption phenomena. In this lecture, I will talk mainly about the basics of heterogeneous catalysis, and I would like to organize your knowledge for the catalyst preparation. Heterogeneous catalysis is a subfield of catalysis in which the catalyst is an aggregation state different from the reactants. Usually, heterogeneous catalysts are solid material speeding up chemical reaction. How to make catalyst? Catalyst preparation can be made tentatively or empirically and requires knowledge and experience. But it also can be optimized through experimental design. On the other hand, the preparation can be made from the basic knowledge like surface phenomena, physiochemical properties, morphology, texture and structure of the different materials involved in the preparation. The main question is, what parameters are involved? The more practical and usual is to obtain the preparation parameter as a precursor salts, methodology, impregnation or precipitation, pH, agent time, contact time, temperature, agitation, concentration, etc. In the experimental design, as we shall see, this parameter can be selected and optimized to be used in the experience. On the other hand, the theory allows us to identify the interfacial and surface physiochemical, geometrical, and electronic parameters. In general, it is desired to know about the adsorption and desorption phenomena, the bond strengths, geometrical and electronic phenomena, which provide reasonable accuracy optimization of the preparation process. Let's start from the beginning. I would like to perform an experiment. Here is a balloon with hydrogen. Air is outside of the balloon. What will happen if I use a needle to have hydrogen mixed with oxygen? I just inject hydrogen into the room. Why a chemical reaction didn't occur? Why red Christmas ball didn't broke? As shown on a figure, a block of mass m and speed v move towards the stationary block m that is have portable wall, and this wall is attached a spring which has spring constant k. After the collision, both blocks are moving, and the spring has compressed and lock at some point, as result storing energy. We have to find final speed after the collision. This is mechanical analog of a chemical reaction. This is a solution of our problem where V1 and V2 is the speed of a block, a difference block, and Q is energy which is accumulate or conservate in spring. This is a very beautiful and very important equations. Let's consider that we take a two Christmas ball, one move in direction to another one with speed v, and the second one is has speed 0. And Q is the energy required to destroy our ball. Which speed need to destroy the Christmas ball? For the first moment you can think that kinetic energy of the first ball has to be higher than Q. It's not completely true. You have to take into account that energy of the first ball go for moving second one. And in this case, to destroy ball, the energy of a center of mass must be higher than Q. Only in this case you have chance to destroy ball. What do you think? Can Q be negative? Now we come back to our molecules. The chemical reaction happens when chemical bonds are created or destroyed. At the most basic level, A chemical reaction involves a breaking, forming, or rearrangement of atomic bonds. Let's consider a simple chemical reaction, the combustion of hydrogen to make water. For this reaction to occur, hydrogen-hydrogen bond and oxygen-oxygen bond must be broken, while hydrogen-oxygen bond must be formed. This bond breaking and bond making process occur at the subatomic scale and involve the rearrangement of bonding electrons cloud between the atoms as they either pull apart or come together. In order to successfully react, molecules must collide at just the right angle and must have sufficient energy to overcome the energetic barrier of the reaction. This minimum required energy is known as the activation energy. The activation energy reflects the point that a certain amount of energy must be supplied in order to break the reactant bond, thereby leading to an activated state, where it then becomes energetically downhill to form new product bonds. In general, only a small fraction of reactant molecules will have this minimum sufficient energy to react. You know that the energetic distribution of gas molecules follows a Maxwell-Boltzmann distribution, and only the highest energy gas molecules in the exponential tail has sufficient energy to successfully react. Summarizing this atomic level picture of the reaction process, we can understand that the overall reaction rate should be given by frequency at which the reactants collide multiplied by the probability that they have sufficient energy to react when they collide. We didn't have success to produce water at room temperature. The most common way that the reaction hydrogen and oxygen can be accomplished is by using a catalyst. A catalyst is a material which participates in the reaction process and thereby facilitate a faster reaction rate, but it is itself not consumed during the reaction. In 1823, de Berenier, he was a famous chemist, discovered that platinum sponge would react at room temperature with hydrogen. This is the de Berenier lamps. The hydrogen is produced by reaction of sulfuric acid with zinc, and this lamp became widely used in industry and even in households. De Berenier's invention can be considered as the first practical application of catalysis. The electrocatalytic analog of the de Berenier reaction was discovered by Grove, who designed a fuel cell in 1839. Grove proved that electrical energy, instead of heat, could be produced from an electrochemical reaction between hydrogen and oxygen over a platinum electrode. He called his device a gas voltaic battery. Electricity was stored by the electrochemical decomposition of water and released by the reaction of the products with platinum. The fuel cell is currently considered as a source of electrical energy in the context of hydrogen-based energy economy, in combination with electricity produced by electrolysis of water and generated by renewable energy sources such as wind or solar. The fuel cell will make the cars as a catalytic vehicle. Did you see catalyst before? This is a picture of catalyst. Very beautiful. Now you probably already guessed that a heterogeneous catalytic reaction proceeds on a surface of the catalytically active materials by making and breaking of bonds between reacting species and the atoms of the catalytic surface. In discussing heterogeneous catalysis, we are therefore dealing essentially with a chemical process occurring in two dimensions. However, the reactant and products molecules have to approach and leave the surface in the three-dimensional process. It is clear that in order to optimize the rate of reaction, the surface area of the catalyst must be high. It must contain as many sites as possible at which the molecules involved in the process can be adsorbed. Further, as we will discuss later, all of the surface, external and internal, must be accessible to the reactant molecules approaching it from the gas phase, and it must be possible for the products to get away from the surface. You have to remember that at least one of the reactants in the all heterogeneous catalyzed process must be attached for a significant period of time to the surface. However, two different mechanistic situations can arise in the surface catalyzed transformation of gas phase species A and B to product C if both species are attached to the surface, the so-called Langmuir-Hesselwood mechanism, or only one of them is bound, and is converted into a product when the other impact upon it from the gas phase, the Eli-Iridial mechanism. I would like to say that the first of these mechanisms hold good far more frequently than the second, that the distinction between them is sometimes fuzzy. It is also helpful to distinguish different way interaction of gas molecules with solid surface. You have to understand difference between physical and chemical adsorptions. Physical adsorption involves the force of molecular dipole and quadrupole attraction-interaction. It is often termed van der Waals adsorption. On the other hand, chemisorption involves the rearrangement of electrons of the interacting gas and solid, with consequential formation and breaking of chemical bonds. Remember that physical adsorption is characterized by enthalpy changes that are small, typically in the range of 10 to 40 kJ per mole, whereas heat of chemisorption are rarely 80 kJ per mole and often exceed 400 kJ per mole. Other distinctions between these two extreme types of adsorption devolve upon the temperature at which adsorption takes place and its specificity. Physical adsorption occurs only at temperature close to the boiling point of the adsorbate, whereas chemisorption has no such restriction. Since chemisorption is chemical reaction confined to the surface of solid, and since chemical reactions are specific, so also are chemisorption in the sense of that if a species is chemisorbed by a given solid under certain conditions, it does not follow that the same gas will be chemisorbed by another solid under identical conditions. What do you think? Which interaction of gas with the solid surface will lead to the catalytic reaction? Did you know that at room temperature the average velocity of the molecules such hydrogen, water and oxygen are respectively 1.8, 0.6 and 0.5 km per second? These facts are derived from the kinetic theory of gases. Gas molecules do not diffuse as rapidly as a very high speed must suggest. If molecules actually move through the room at 100 meters per second, we should detect odors faster than we hear sound. Instead, it can be taken several minutes for us to detect an aroma because molecules are traveling in a medium with other gaseous molecules. Because gas molecules collide as often as 10^10 times per second, changing direction and speed with each molecule, they do not diffuse across a room in a straight line. At 1 atmosphere and room temperature, for example, and oxygen or nitrogen molecules in atmosphere travel around on about like 60 nanometers between collisions. It is clear that we are particularly interested in surface reaction and catalysis. We have to know the rate of collision between gas and a solid surface. What is the frequency of collision per surface unit? I will give you some reminders. The surface A perpendicular to the x-axis. A molecule whose velocity component along x is positive strikes the surface at the time delta t if it is at a distance less than or equal to the x delta t of the surface. If n is the number of molecules per unit volume, then there will be n a Vx delta t molecules in this volume. The average number of collisions against the surface during the time delta t is equal to the average number of molecules in the volume a Vx delta t multiplied by the probability density of this velocity. Average number of impact against the surface A equal. On the other side, n being the number of molecules in the corresponding volume V, we have n number equal, taking A as a 1 square meter and delta t is 1 second, we have frequency of collision per surface unit equal P divided by square root 2 pi m chi t. This is a very useful equation. However, the rate of adsorption of gas on a surface is determined by the rate of collision between the gas and the surface and by the sticking coefficient. Sticking coefficient is a ratio of the number of adsorbed atoms or molecules that adsorb or stick to the surface to the total number of atoms that collide upon the surface during the same period of time. We have to see, however, that the sticking coefficient varies with coverage. Sometimes sticking coefficient is seen to vary in this linear fashion with coverage, but frequently it's dropped non-linear. See figures on a slide. What can be a catalyst? It was Berzelius who first used the word catalysis in 1836. By definition, catalysis is a process by which a reaction rate is enhanced by a small amount of catalyst that supposedly does not undergo any change during the reaction. However, this is a too optimistic definition, as real catalysts change in structure, activity, selectivity with time on stream and deactivate it more or less rapidly. Some 60 years after Berzelius, Oswald established the kinetic nature of the phenomena and in 1895 gave the definition. A catalyst is a substance that changes the rate of chemical reaction without itself appearing in the products. As I said earlier today, catalysis starts with chemisorption, which should not to be strong to permit intermediate formation and the intermediate desorption to product, nor too weak to permit adsorbed species to be activated, which is known as the Sabatier's principle. Sabatier formulated a chemical theory of catalysis that involves the formation of unstable chemical compounds as intermediates. This determines the product selectivity and the rate of the catalytic reaction. She assumed that the hydrogenation reaction catalyzed by nickel involves various nickel hydrates with concentration that relate to the reactivity of the nickel. He argued that the formation and decomposition of intermediate compounds formed between reagent and catalyst corresponded to lowering of the Gibbs energy of the system. This view is completely validated by modern molecular insight in the action of catalyst. It is a rule that Sabatier formulated the condition of optimum catalytic reactivity. In a catalytic reaction, reacting molecules form intermediate complex with the catalyst. This complex should be of intermediate stability. If they are too stable, they will not decompose to achieve product formation. If they are too unstable, reagent molecules will not be achieved and the surface reaction intermediate complex will be not formed. As we know now, the catalytic reaction is composed of a sequence elementary reaction step. Molecules adsorb on the catalyst surface, where they become activated and form intermediate reaction complexes. These complexes then rearrange and recombine. Final product formation occurs by desorption of the product molecules that generated the free catalytic surface sites. Sabatier rules is a direct consequence of the cyclic nature of the catalytic reaction sequence. This leads to the volcanotype dependence of the overall catalytic reaction rate of catalyst reactivity as shown on a figure. Later on, Taylor has suggested that activation energy was conserved during the adsorption stage. He also suggested that preferential adsorption of the catalyst surface should take place at those atoms or ensemble of atoms, depending on the reaction and reactant size, situated on the peaks, fissures, kicks, edges, etc. of the crystal rather than on the flat surface. His notion of the active site or active center was then suggested to the location of the catalytic conversion. In the case of metals, active sites are often taken as each surface metal atoms. However, depending on the reactant molecule size and reaction, more than one surface atom may be involved in the reaction. This is what was defined by Boudard as a structure-sensitive reaction. What can be a catalyst? Catalyst can be metals, oxide, sulfide, carbides, nitrites, acid, salts, virtually any type of material. The main objective of using catalysts is to get high activity and overall high selectivity to desired product. The latter property avoiding or limited separation purification procedure, which involves important processes to take into account for environmental issues. Suppose that our tests in laboratory have yielded a formulation with excellent activity in terms of turnover per active sites for a certain product and fabulous selectivity toward desired product. Will the substance be a successful catalyst in industrial application? Not necessarily. It will have to be developed into material with the following main properties aspected of the catalyst are given in this slide, and this is I will ask at exam. You have to remember that catalysts are generally developed for a specific process, that is, for a certain reaction in a certain reactor under certain conditions. One of the most important classifications of heterogeneous reaction is the one that divides them into structure-sensitive and structure-insensitive reaction. In structure-sensitive reactions, the turnover rates per surface atom of the catalyst depend on the size of the catalytic particles. For the structure-insensitive reaction, every surface atom is equally active. Single crystal studies have clearly shown that the rate of such reaction, for example, as ammonia synthesis, strongly depend on the structure of the metal surface, while alkane hydrogenation has been found to be insensitive to surface structure. The figure shows these three types of reaction. Hydrogenation reaction are of the type 1 and are structure insensitive, behavior that is widely reported for hydrogenation of olefin as well as aromatics. In contrast, the turnover rate for CH bond activation, for example for ethane hydrogenolysis, decreases when particle size is increased. This is a type 2. The third type occurs at CO hydrogenation, in which the K reaction is a cleavage of the strong triple CO bond. It has been observed that the turnover rate increases with particle size, and sometimes it also shows a maximum at intermediate particle size. Beta dispersed particles expose comparatively more corners and edges atoms than atoms that make up the surface facets. A very important example of this type 2 behavior is found in the activation of methane. Several studies have shown that the rate of steam methane reforming, which is controlled by the activation CH bond, increased strongly with particle dispersion for a wide range of transition metal, including platinum, rhodium, iridium, and palladium. The structure and geometry of the surface play a dominant role with respect to its reactivity in adsorption and catalysis. An important parameter for surface reactivity is the density of atoms in the surface. The general rule of thumb is that the more open the surface, the more reactive it is. Definition on the most common adsorption site are shown in the slide. They are named on the top side, bridge side, hollow side. For example, the hollow side may be threefold or fourfold in character. The number of adsorption sites on a surface follow from their geometry. In material science and engineering, we use the concept of lattice to describe arrangements of atoms and/or ions. The unit cell is the subdivision of lattice that still retains the overall characteristic of the entire lattice. Unit cells are shown in the slides. By stacking identical unit cells, the entire lattice can be constructed. There are 7 unique arrangements known as a crystal system, which can be used to fill up a 3-dimensional space. These are cubic, tetragonal, orthorhombic, rhombohedral or trigonal, hexagonal, monoclinic or triclinic. Also, there are 7 crystal systems. We have a total of 14 distinct arrangements of lattice points. These unique arrangements of lattice points are known as the Bravais lattice. Lattice points are located at the corners of the unit cell and, in some cases, at either face or center of the unit cell. The lattice parameters, which describe the size and shape of the unit cell, include the dimensions of the sides of the unit cell and the angles between the sides. In a cubic crystal system, only the length of the one of the side of the cube is necessary to completely describe the cell. This length in the lattice parameters are 0. Several lattice parameters are required to define the size and shape of complex unit cell. For an orthorhombic unit cell, we must specify the dimensions of the 3 sides of the cell, I0, B0, and C0. Hexagonal unit cell require 2 dimensions, A0 and C0, and the angle of 120 degrees between the A0 axes. The most complicated cell, the triclinic cell, is described by the 3 lengths and the 3 angles. We can locate certain points, such as the atom positions, in the lattice or unit cell by constructing the right-handed coordinate system. The coordinates are written as the 3 distances which comma separated the numbers. Miller indices for direction are the notation used to describe the directions. Here presents the procedure for finding the Miller indices for directions. Using a right-hand coordinate system, determine the coordinate of 2 points that lie on the directions. Subtract the coordinates of the tail point from the coordinates of the hand points to obtain the number of lattice parameters traveled in the direction of each axis of the coordinate system. Clean fraction and or reduce the result obtained from subtraction to lowest integers. Enclose the number in a square brackets. If a negative sign is produced, represent the negative sign with a bar over the number. Miller indices are used as a shorthand notation to identify the important planes. Identify the points at which the plane intersect the x, y, and z in terms of the number of lattice parameters. If the plane passes through the origin of the coordinate system must be moved. Take reciprocals of these intercepts. Clean fraction but do not reduce the lowest integers. Enclose the results number in the bracket. Again, negative number should be written with a bar over the number. The following examples show how Miller indexes of plane can be obtained. Bulk structures of oxide are best described by assuming that they are made up of positive metals ions, cations, and negative or ions, anions. Reaction with oxide may involve the atomic oxygen on the network, especially for the selective oxidation reaction. Indeed, the oxygen anions have a weak link with the sublayers which during the reaction can be incorporated in the adsorbed molecules. Ionic oxides are represented by cation and anions, and the formation of ionic surfaces occur by disruption of the bonding with the formation of uncompensated charges. Having positive charge, electron acceptor forms Lewis-type sites, while with excess of negative charges form Bronsted-type sites. In fact, the heterolytic molecules break on oxide, while on a metal they are neutral. Many gases adsorb only after heterolytic dissociation. Hydrogen interaction only weakly with most oxide surface. If the surface is sufficiently reactive, heterolytic splitting occurs. Water dissociation readily into hydrogen plus OH minus on almost all oxide surfaces. This leads to two different hydroxyl groups, a terminal one which a basic character on the cation and a bridging which acidic character. In hydrocarbons or alcohols, the CH or H bond usually break readily, while CC bond are most difficult to activate. The mechanism of oxidation reaction involves oxygen of the lattice is well known as Marz-van Crevelen mechanism. An effective catalyst may have many different types of active surface species, and each will be capable of catalyzing reactions. Metal species are mostly commonly used for reaction of the hydrocarbon, example being hydrocarbon reforming or steam methane reforming. Oxides are used for different types of reaction as well, and typical selective oxidation reaction. However, as the oxides have exhibit acidic or even basic property, they are also used for reaction require the acid or bases. A typical example being catalytic isomerization of hydrocarbons. And sulfur can be used for reaction involving sulfur-containing molecules such as hydrodesulfurization. In order to obtain high surface area and hence increase the rate at which the reaction occurs, it is desirable to obtain highly dispersed material. The slides show what happens when a solid of cube form and which side of length 1 cm is divided into smaller cube of side half centimeter. The original cube has a surface area of 6 square centimeter, while the 8 small cubes have a total area of 12 square centimeter. If the side of cube is 1 nanometer, the area of material is now 6,000 square meters, and increase the area by factor of 10 power 7. The same factor will apply to the increase the rate of catalytic reaction. Catalytic reaction proceeds on a surface of the catalytically active material. In order to optimize the rate of the reaction, the surface area of the catalyst must be high. Let's step back a little bit here. It is common knowledge that the falling raindrop has a shape. What is the shape of a raindrop? May I ask you to draw a raindrop falling from the clouds before end of the music? Could you choose the shape A, B or C?
I'm singing in the rain, just singing in the rain. What a glorious feeling, I'm happy again. I'm laughing at clouds so dark up above. The sun's in my heart and I'm ready for love. Let the stormy clouds chase everyone from the place. Come on with the rain, I've a smile on my face. I'll walk down the lane with a happy refrain, just singing, singing in the rain.
Around 99% of you would draw it like a tears drop exiting the clouds. The weather forecast on a television depict raindrops as a teardrops which lead to common people being accidentally educated. The raindrops have that shape. Meteorologists have known for years that an actual raindrop bears no similarity to a teardrops. The results obtained by picturing a small drop less than 1 millimeter in diameter using high-speed photography shows that raindrops are almost perfect shapes. If you increase it by 100 times or so, the largest version would resemble a hamburger bun. Why the drop is spherical? The answer to that lies in a simple phenomena known as surface tension. A liquid will have a minimum surface energy if it exits as a spherical drops, as this will have the minimum surface area for the given drop size. Two separate drops will tend to merge to form a single one, hence minimizing the total surface energy. As an example, if two soap bubbles are connected to one another by a tube, will the bubbles remain the same size? The answer is one will get smaller and the other larger until the surface area of the two bubbles added together have a reached minimum. All materials have surface energies, these being equivalent to the surface tension of liquid. Just as with a liquid, the surface area will tend to try to minimize itself in order to reduce the total surface energy. This means that the particles will have tendency to merge to reform the original cube. We have to find some way to stop that happening. You have to remember that this agglomeration of the particle will be particularly important if the temperature is near the Taman temperature. Taman temperature is the temperature at which atoms of the solid become mobile. The agglomeration process is known as a sintering. While sintering is desirable in some application, for example in ceramic manufacture, in the case of heterogeneous catalysis, any sintering will cause loss of catalytic activity. So-called Taman temperature is a temperature of 0.6 of melting point for these materials. One way to prevent the sintering of catalytically active component is to fix the particles onto another high surface area support, in such a way that the particle cannot come into contact with one another. The most commonly used support materials are oxides. They are metal oxides that have high melting point and are therefore very stable under most operation conditions. This slide shows values of the melting points and the Taman temperature for the series of different oxides commonly used as a catalyst support. Some of them also used as a catalyst promoter to prevent sintering. Supported catalyst consists of a catalytically active phase dispersed over a support. This is the most important class of solid catalyst. The catalyst use supports such as a silica oxide or aluminum oxide, and the active nanoparticle consisting of metal, metal oxide or metal sulfide with a size typically from 1 till 10 nanometers. Suitable promoters are frequently added to obtain adequate performance. They may either modify the catalyst structure, so improve stability, or enhance the catalyst reaction to give better activity or selectivity. However, the nature of the active species is always the most important factor. Could you investigate this table as a homework? As a heterogeneous catalyst is a composite material characterized by the relatively amount of different compounds, active species, physical or chemical promoters and support. The optimum catalyst is the one that provides the necessary combination of property, activity, selectivity, lifetime, ease of regeneration and toxicity at an acceptable cost. These requirements are in the many cases a conflict, and catalyst design mainly consists of the achievement of the suitable compromise. The so-called bulk catalysts contain mainly the active component by mass which electronic and structural promoter added it. The iron-based ammonia synthesis catalyst is a prime example of such bulk catalyst. For the preparation of heterogeneous catalysts, two principal methods exist. First one is the impregnation of existing support with a solution of precursor of the active metals. And the second one, so-called co-precipitation, where one or more metals are precipitated together with the support of its precursor. The first method is not only used in the lab scale, but it also widely applied industrially. It is relatively easy to perform and does not require complicated or expensive equipment. However, for a number of catalysts, co-precipitation can be very attractive, and the large number of commercial catalysts, for example, catalysts for methanol production, steam reforming, water gas shift reaction, are produced in this way. This method is often considered to be more difficult and indeed requires an accurate control of condition and enhance the use of more complicated equipment. All catalyst features like surface area of the active phase, porous structure, particle size and shape, etc. are strongly depend on the process condition, like the nature and method of dosing of ingredient, mixing and stirring. Therefore, these conditions have to be accurate control throughout the precipitation procedure. as complication is not, probably no signed condition exists that is optimal for all of the above processes. I would like to finish today. Next lecture we will discuss the catalyst preparation. I will give the example of some of the most common use approach to the preparation of the support and catalysts.